Assignment 29 is 4.5, derivatives of inverse trigonometric functions. Your essential question is, how do you find the derivatives of the inverse trig functions using implicit differentiation? So a couple of important things that we're going to have to remember here is, first of all, what are inverse functions? And then we'll be introduced to what implicit differentiation is. Okay, so let's start with inverse functions. So I think that we've used inverse functions the most when we talk about exponential functions and logarithmic functions and how they're inverses of each other. So there are other types, but let me give you some pictures. So in your book, on page 147, here's a graph of a function, population versus time. And so when we take this original function, and if we want the inverse of it, it's always that graph that is going to take every point on the original function and it's going to reflect it across the line y equals x. And that's because every point on the original function, well, on that inverse function, the x's and the y's have been switched. Okay, so that's basically your inverse function, and there's some notation. So this is on page 148. You have some definitions, and I'm going to write some of this stuff down just to remind you. But basically, if you have an inverse function, so if y equals f of x, then your inverse is where you basically switch out your x and your y's. Okay? And I'll come back to this in a second. Well, actually, let's talk about this now. So if you take your function and you do the inverse of it and you still get a function, then it's said to be invertible. That's not really important, and I've never brought that word up before, okay? But then if you actually get a function, if your inverse relation is actually a function, then you can write it using that inverse notation, right? So f to the negative 1 of x, okay? So that's how we actually notate inverse functions. And if we take the inverse function and plug it into the original function, we'll get x. And the same thing is true if we take our original function and plug it into the inverse function, we'll also get x. And that's how you know when two functions are inverses. And of course, the graphs of the function and its inverse are going to be reflected across that line y equals x. Okay, so I'll jot down a couple of those notes for you. So let me do an example here. So an example of an inverse function. All right, so I'm going to start with f of x is going to equal 2x minus 4. And when we're dealing with inverses, it's usually easier to think of f of x like y, because then you're just dealing with one variable as opposed to this f of x. So when we want to find the inverse function, we just switch the x and the y. And then we solve for y. So I'm going to have, let's see, a negative 2y equals a negative x minus 4, and divide by negative 2. So a better way to write this then is to say, well, this is f to the negative 1, or f inverse of x, will equal 1/2 x plus 2. Okay, and so these two, right, this is the original function, and then this is its inverse. Okay, so a couple of important bullet points that we'll do here. Let's see, I'll go down here. So we're going to have a reflection in the line y equals x. So one way to do that is to visualize it when you're graphing. Like if I graph this original function, I can visually try and reflect it. Or the other thing is, any point that's on this function, well, the points on this are just going to be the x and y switched. Okay. All right, another thing, or the same thing, I should say. So if I take those x and y's from the original function, then my inverse function, I just switch them. So my points on my inverse function look like this. Okay, so this is the original, this is the inverse. That's how those points are related. Okay, and then the last thing, or the last thing I'm going to cover anyways, to refresh your memory, is that if I take that inverse function and I plug it in to the original function f, I'm going to get x out. And also, if I take the original function f of x and plug it into the inverse function, I'm also going to get x out. So I'm going to use our example that we did up here and show you that in fact they truly are inverses of each other. So starting with the original function, wherever I see an x, I'm going to plug in the f inverse, or the inverse function. So I will take 2, and instead of having x there, I'm going to plug in 1/2 x plus 2. And from there I'll minus 4, since that's part of this original equation. So distributing, I get x plus 4 minus 4, which is going to equal x. So it's working when I plug the inverse function into the original function. And now we'll double check that it works the other way around. So taking my inverse function and plugging my original function in wherever I see x. So I get x minus 2 plus 2, and in fact, they are inverses of each other because when I plug them into each other, I get x. Now, in the example I showed you earlier, we had the original function and the inverse function. And they both ended up being functions, right? They both, if you think about it, every single input only has one output. So let's think now about our trig functions. So our trig functions are, I'm on page 149. Okay, you can see that the trig functions, that is not true. When I take the inverse of any trig function, so here's the inverse sine function, you can see that you get this squiggly line, this wave. Okay, the problem is going to be, is this going to be a function? So if I put 1 in, I tend to get out a couple, or many, because this goes on forever, outputs. Okay, same with the inverse tangent function, right? Just think about input 1. How many outputs do I have? Many. Okay, and that continues on. So what ends up happening is we have to define these inverse trig functions. We have to define a principal branch. So that principal branch is going to be the branch that is closest to the origin. So you'll notice the dotted line is part of the function that we have gotten rid of. So the principal branch of the inverse sine is just as closest, so that our domain here is from -1 to 1. And our range is from -π/2 to π/2. Okay, and so forth. Okay, so it's really important that when you do the inverse of any function, if you're trying to actually determine if the inverse is a function, and if you're trying to treat it like a function, then you have to restrict it so that it actually is, in fact, a function and has, one input has one output. Okay, so one more thing I want to go over before we get started on actually taking the derivative of inverse tan, is I would like to talk about implicit differentiation. So this is new to you. And we are going to use it quite often. And it's probably not the easiest thing. Okay, but it's also, you'll get used to it, and it will become pretty obvious to see. So what you want to do when you do implicit differentiation is you differentiate, or take the derivative, both sides of an equation with respect to x. There might be other variables in there, okay? But it's important that you're always saying with respect to x. So like dy dx, dt dx, dc dx, whatever variables are in there, you're always doing it with respect to x. All right, so let's do our first example. We are going to differentiate y equals tan inverse of x. And one thing I haven't gone over is that another way of saying these is arctan or arcsine. So all of the trig functions, if you don't want to say the inverse of tan, you could say arctan. That's the same thing. So maybe I'll write that here. So this is also known as, or aka, y equals arctan x. Okay, so step 1 is to rewrite in terms of tan. Okay, so basically I'm going to take this and I'm going to do the inverse. So I'm going to switch x and y. Okay, so I'm going to have x equals tan y. Okay, second thing we're going to do, we're going to take the derivative using implicit differentiation. I'm going to abbreviate because I'm out of room here. Implicit diff. Okay, so I'm going to rewrite this. And so basically what I want to do now is I want to take the derivative of both sides with respect to x. So on the left side, I'm going to take the derivative of x with respect to x. Then I'm also going to take the derivative of tan y with respect to x. So on the left side, I just get 1. On the right side, however, what I end up with, well, the derivative of tan y is going to be secant squared y. Then I need to chain rule this. So I need to take the derivative of the inside function. So that's the same thing as dy dx. Okay, so I just took the derivative of y with respect to x. All right, next step. Step 3. We are now going to solve for dy dx. Right? Because originally what I wanted to do was I wanted to take the derivative of y here with respect to x. Okay? So I'm using inverses to help me, and I'm using implicit differentiation to help me. All right, so doing that, I basically need to get this by itself. So I'm going to divide both sides by secant squared y. So 1 over secant squared y will equal dy dx. So remember now, 1 over secant squared is the same thing as cosine squared. The problem that I have right now is that my dy dx, if I'm taking the derivative with respect to x, x needs to be my input. And right now, y is my input. So I need to deal with this. Okay, and the way I'm going to deal with this is to use my trigonometric ratios, my sine, my cosine, or my tangent. So if you guys remember, your SO, or your CA, or your TOA, where sine is the ratio of opposite over hypotenuse, cosine is the ratio of adjacent over hypotenuse, and tangent is the ratio of opposite over adjacent. Alrighty. So this is going to involve, these are right triangle ratios. So I'm going to go ahead and draw myself a right triangle. Now the important part is that when I think about tangent, we have restricted our range to be from negative pi over 2 to pi over 2. Okay, so that's basically from negative 90 degrees to positive 90 degrees. So it's going to be important then that I restrict where I might draw this right triangle. So if I draw it in the first quadrant, right, this is between 0 and 90 degrees, or 0 and pi over 2. So this is why I'm going to go back to my original equation, which was x equals tan y. And remember, tan is opposite over adjacent, okay? And so I have this right triangle standard position. I'm going to have the angle be y, that's the input of tangent, okay? And then that is going to be opposite over adjacent, and the ratio of that would be x over 1. So if I want cosine of y, well, that's adjacent over hypotenuse. I'm missing the hypotenuse here. So I have to actually I have to come up with the hypotenuse. So I have a right triangle, luckily, and I remember my Pythagorean theorem, luckily. So this is basically the hypotenuse squared will be 1 squared plus x squared. So my hypotenuse is actually the square root of 1 plus x squared. So now when I want cosine of y, or also cosine squared, but let's just talk about cosine. Cosine is going to be of y is going to be adjacent over hypotenuse. So now I've got 1 over the square root of 1 plus x squared equaling, almost, I messed up, I need a squared because it's cosine squared, right? So squaring this is going to give me dy over dx. Okay, and then one last step, I can actually square these things. So 1 squared is 1, and the square root of 1 plus x squared, if I square that, I just get 1 plus x squared. And that is the derivative of y with respect to x for the inverse tan. Okay, so I've made you suffer long enough. Now you need to be able to do this. Okay, you need to be able to come up with the derivative of these guys using implicit differentiation. Okay, going through this. However, you can also memorize them or write them on a note card. So here they are. The derivatives of the 6 inverse trig functions. So I would definitely have this on a note card for every test you ever take with me. So the derivative with respect to x of sine inverse, or arc sine, is going to be 1 over the square root of 1 minus x squared. We just did the tangent one, the derivative with respect to x of tan inverse of x will be 1 over 1 plus x squared. The derivative with respect to x of secant inverse, or inverse secant, is going to equal 1 over the absolute value of x squared minus 1, the square root of that. Okay, and now I'm going to do all of the c's, because guess what happens to these? So they're basically going to be the exact same thing, but every time we take the derivative of one of our trig functions with a c, it becomes negative, right? So that's exactly what's going to happen here. So the derivative with respect to x of cosine inverse will basically be the exact same thing, just with a negative. The derivative with respect to x, of cotangent, cotan inverse, will end up giving you a negative 1 over 1 plus x squared. Right? Same exact thing, just a negative sign. And then the last one, the derivative with respect to x of cosecant inverse of x will end up being the exact same thing, just with a negative in front. So let's do one together from your book. So how do you use these? So let's do number 13 from your textbook. Y equals sine inverse of 4x, and we need the derivative of that. So y prime, okay, well let's see. So sine inverse is going to be this. So basically wherever you see x, you put whatever the input of your sine inverse function is, which is going to be 4x. And it's that easy, okay? You still have to chain rule, but it's pretty much that easy. So I'm going to use this right here. It's going to be 1 over the square root of 1 minus, and instead of x, I'm going to put 4x, but it's 4x squared, times, I have to chain rule that, so I need the derivative of this inside, which is 4. So I basically get 4 over the square root of 1 minus 16x squared. So it's a lot easier than actually deriving these derivatives, right? But there will be times for deriving them, and there will be times where you can just use the formula that you're given here.